So in the first week of class and the second week of class, we didn't do a whole lot of programming. We focused more on how you go about the process of programming. And this algorithmic design with object-oriented programming kind of builds on that. But we start looking at it within the context of things being objects. How do we design an algorithm thinking about things object-orientedly, if that's a term? So let's go ahead and take a look at that. So, given a problem description, what steps should you use to implement its solution? Well, you need to decide on the classes and the objects that are needed. So you need to think about this kind of the structure of everything. And then for each of the classes, you need to decide on the instance variables that are required. And then for each class, you also need to decide on its public methods, or what we would call the interface. And then finally, for each of those methods, you need to implement it using top-down design. And so what is top-down design? Well, when you're writing a public method that's fairly large and involved, you can break it down into subtasks, right? As we currently already saw using the helper methods. So you'll write your public methods out, and then you'll call these helper methods, but you won't fully flesh out what those helper methods are, okay? You'll just kind of help define them. And so why is this beneficial? Well, you can postpone worrying about the details of each subtask's implementation. So you can focus on the big picture first, and then it allows you to worry about the details as you get later on. Now, focusing on the big picture is crucial, because if the big picture is wrong, then the whole thing is wrong, right? So you want to kind of start large, start with the camera zoomed out, think about the problem of what you have to do in its totality, kind of think about, okay, the big picture things. And then you're going to define what those big tasks are, and then you're going to break it down into smaller tasks, and then say, okay, well, what are those tasks? And then you're going to break those things down even further and say, okay, well, what do those subtasks need? And so on and so forth. So that's top-down design. And it's used in the acquisition world a lot, and except for it's called a work breakdown structure. You're going to break a task down into subordinate tasks, and it makes it easier to track and manage, which all those things are. So let's take a look at a practical example. We're going to write a program that calculates the estimated cost for building a building, right? So if we're going to do this, we're going to do it in a top-down manner. We're going to calculate the cost of different rooms in the house, right? Or building, whatever it is. So we're going to have to calculate the cost of the bathrooms, as you can see shaded here in blue. And we're also going to have to calculate the cost of other weird rooms like studies and porches, right? Maybe we have to calculate a bedroom. So at this point, we haven't necessarily defined what those methods are yet. I mean, we define what they are, but not what they do. We just know that we need to calculate the rooms, right? So we just start defining them once we have all of those general methods written out. So, of course, here we're going to have other methods like calculate bedroom or calculate hall or whatever, right? This is just an example. And then we're going to break down each of those. And we'll know that they have to do some stuff that's similar. Like, since both methods are going to be calculating floor space, that's going to be a good calculate to pull out into a helper method, right? So we can pull this functionality out and say, hey, you know what? This is going to be its own separate method. And we can do that separately. So generally, if two or more methods perform the same subtask, we're going to avoid the redundant code by having those methods call a shared private helper method, as we've already discussed. And so in class, we'll work on doing an example of this. As you're doing this top-down design, a critical feature or functionality to have is stubs. And stubs are basically parts of a program that they're going to occupy space that a function will do, even if it doesn't execute it entirely. So let's take a look at what a stub is exactly. After writing your entire program in pencil on paper, right, you're going to do your pseudocode and all that stuff, we're going to enter it into a computer using stubs for subtask methods. And a stub, like I said, is just a dummy method that looks like this, right? We're going to have this method called do something cool, and instead of actually doing something cool, we're just printing out do something cool. We haven't actually given it any functionality yet, right? So what are the benefits of using stubs? If the program is initially entered with stubs, then the programmer will be able to more easily get an initial successful compilation. And that leads to that warm fuzzy feeling. It gives you confidence as you're building your program. And this is a great thing to do, especially as you're learning, is you're going to be entering lots of debug lines, like this right here, system out print line, do something cool, right? You know that you've entered that method when you've called it from something else. And so you'll pop it up on the console and says, hey, I've entered this method. Also, after the program is successfully compiled and run with the stubs, then we can replace the stubs with actual code one method at a time. And ideally, after each method is replaced, it's thoroughly debugged. That way, if a bug appears, it's really easy to find where it's at because you know that you've only done work in this method right here. It's like, hey, the program was working just fine when all it did was print out, do something cool, but now I've added in some additional stuff down here and it broke. So you know where to do it. So this is one thing I try to tell the students is, always make sure that you enter a line of code and if possible, compile it then so that way you can find out where you're breaking something. Don't write 30 lines of code and then try to compile it and then get 40 errors because they're going to multiply. They're going to have little, bug babies and it's just a mess. So compile often and frequently so that way you can find out where it is that you've messed something up because you inevitably will. It's not bad. It's just part of the learning process. So up to this point, for each of our object-oriented programs, we've had our classes split up into two separate files. We had a file that described an object like mouse or car, or in this case, shirt, right? And then we had a separate driver file called mouse driver, car driver, or in this case, shirt driver, right? And you can see here that in this driver, the only thing that we've really got going on is this main method, right? Where we create an object and then we do some stuff. Well, instead of doing that, for short programs that don't really do a whole lot, it's a lot easier if we just do away with the driver program and just include it into our class. And you can use it for testing purposes as well as just to make things a little bit more streamlined and less clutter with having two files. Now you can condense it down into one. But generally, you only do this for very small classes. Now, here we have the time class that has three separate members, hours, minutes, and seconds. And see, there's no comments here because it's self-explanatory, right? I know what an hour is. I know what a minute is. Here's our constructor where we're setting what those objects are. We have a method called printIt using your very favorite, bestest method ever, the printf. I know you guys love it, and I know you love reading these strings, trying to figure out what they do. You might want to do that. And here we have our main method, right, where it's going to essentially be our driver class. It's just creating a new time object and we're printing it, right? So we create a new time object at 3 hours, 59 minutes, and 0 seconds, and then we print it. So from the main method, we can create an object of the same type inside of the main method. So we're in the time class and we are creating a time object inside of that. So it's very very meta, very recursive in a way, but it's really not. So the whole point of this is that you can simplify things by including a driver class inside of the class if you don't want to have two separate files. Generally, for class, we'll have two separate files, but this is just something to be aware of. And it's useful for testing. Now, all along by and by, we've been using the this keyword when accessing instance variables. Now, let's cover that a little bit more in depth and show you when you have to and when you don't have to. All right, so here we have the mouse shortcut driver and we have the mouse shortcut class. And I know I just got done talking about you can do this with only one class, but like I said, we're going to mainly stick to using it in 2 different classes. So we have this very simple driver class that's just going to create this new mouse with these 2 arguments and then print it out. All right, so let's go take a look at the mouse shortcut. Now, the use of this within an instance method or constructor to access the calling object's instance variables, right? That's the point of this. Notice here, within our constructor, we're calling set age and set width, or weight, excuse me. Note that we're not calling this dot set age and this dot set weight, right? We could, right? It compiles just fine. We can get rid of it. It compiles just fine, okay? So when do you use it and when do you don't? So the this reference distinguishes instance variables from other variables, like local variables and parameters, that happen to have the same name. So if there's a parameter or local variable with the same name as an instance variable, then you must use this, that's the keyword this, in front of the name to refer to the instance variable, and use the name by itself to refer to the parameter or local variable. However, if there is no ambiguity, then you may omit the this prefix when accessing the instance variable. So here we have set age and set weight. Age, we pass in A, right? Age equals A. Works just fine. But notice here when we pass in the weight, we have weight as the actual name, and we have this dot weight. So here we have the ambiguity, right? We have this instance variable called weight, and we have this local variable called weight. So we have to tell the compiler which one we're talking about. And that's what this is for, right? So pretty straightforward. Again, you could, if you want to help keep things clear in your own mind, you could always use this when referencing an instance variable and also instance methods as well. But you don't have to. So you just have to know when, and that's when there's an ambiguity in the variable names.